Okay, the last concept that we need to discuss and wrap up all the concepts for organic chemistry will take place today, because after this week, next week we'll start the carbohydrates, which means we go to the biochemistry side. And not that one side's better than the other. By this time you should have somewhat of an idea whether you like organic chemistry better or inorganic chemistry, which was last year. Some of you like the numbers better and the periodic table and dealing with the elements. Maybe some of you rather deal with just carbon, hydrogen, oxygen, and nitrogen. I mean, whichever, I don't want to say float your boat or whatever, but some of you will be taking more than one semester of this perhaps in the near future. Okay, and this was on your vocabulary evaluation. It was called a hemiacetal. And excuse me, and the reason that we save it till now is because that is what a lot of the carbohydrate structures look like, is because they end up being what's called a hemiacetal. So I've always had the belief that even though we're going back to aldehyde structures, I think it's important to do that step just before we move on to the carbohydrates. So this also happens with ketones as well, because if someone is claiming or they're on a ketose diet, does that mean anything to you? Ketose does mean ketones, but in this case it means ketose sugars, and that can be, I believe, I don't know, is it fructose, I believe, okay? So they're watching their intake of that type of sugar would be my belief on what they're actually doing. So in this case, if we had ethanol, okay, not ethanol, but we'll just say ethanol. What does that tell you when you see this, okay? Just to make sure that we understand we're pronouncing this right. So what does that tell you right now? It is an aldehyde. So we've got two carbons. Okay, and this is called a what group that resembles acids, esters, ketones? No, I mean in general, this type of carbon. Carbonyl carbon, okay? Because it just means that you have a carbon double bonded to a hydrogen. Or, I hope not. A double bond oxygen to a carbon. Okay, so when this happens in this process of what we call, you can have full acetals, because that was one of your terms, you just didn't use it. Hemiacetal was, let's say, one of your answers that you did put on there. So what happens in here is, you know, for some reason I only put parentheses around plus in this class. I don't do it in the general chemistry or physical science. Is that odd? Okay, yeah, I don't know, it doesn't make any sense to me either, I guess. Okay. So in this case, I always got to think about this, okay? We'll just keep it simple with methanol now, okay? Why don't I put that up here? Methanol now. I think this marker's almost had it. So what is this telling you then? Yeah, OL. That's what you're trying to tell me. Sorry. I knew what it was supposed to say, but I wasn't thinking when, I can see why that would be confusing. There we go. I don't know if that marker's any better. It's supposed to be brand new. So now what does this tell you then? Okay, so we've got an alcohol, and do this because I think it'll make more sense this way. And okay, so we can see we got all those distinct colors there. Okay, we got some blue, some green, and then whatever color this is. So what happens is when you add an alcohol to this aldehyde, we're not really concerned about the catalyst. Okay. This, and what did it say about trying to attach an oxygen on that stigmasterol from yesterday? There's different ways that you can do it, but it was high temperatures, high pressures, and different types of catalysts. But what one of the professors was saying is that those will attack other different types of carbon atoms on that ring. But in this case, to attach an oxygen on site 11, was it? Okay. So oddly enough, the human body can do that very efficiently. But to actually have the enzyme to even make something like that, I don't know if that technology was even available, but to even know how to do this with this compound of stigmasterol is knowing that that was just one step away from different types of hormones you wanted to synthesize. And with this, what is it that naturally, in the human body, what will take stigmasterol and make cortisone? Yeah, it's a type of mold that actually produces the enzyme that will do that. Okay. So in this case, the reason that we've got these color-coded is now this reaction is going to proceed. And this will all remain the same. What's going to happen, okay, this double bond then is going to break. Okay. So there's our oxygen. And I somewhat goofed on this. This should maybe be blue, but I think that'll be okay. So then this hydrogen, okay, is going to reduce this double bond here. So that's where that will go. And, okay. And then this hydrogen is still here. So then now that this double bond is broken, this carbon has one more spot that can form a bond. And then what do we have left over from here? This hydrogen reduced this, okay? So then what do we have left over from here? Say that again. CH3O, is that? Okay, that's what I thought I heard, but I wasn't quite sure. And then that's what actually happens. Okay. So we need green and blue. And then we got CH3. This is what we call this. That is now a hemiacetal structure. Okay? And I'm not quite sure what the real definition was that you had on your paper, but I'm be led to believe that maybe it was R to R and then OCH3 on the bottom. I'm not quite sure what. An OH and okay. That makes sense because here's your OH, then here's your OR group. Now, when we say OR, that doesn't necessarily mean a methyl group. You could also have not just methanol, but what else do you think you could put here? You could put ethanol, you could put propanol. That's an O. Okay. And then I don't think you'd really go much further than that because there's just, of course it's possible, we're just not going to go much further than these three compounds here. Everything gets added to it. That's right. Okay. Not that you want to see the reasoning behind this, but maybe you do. Maybe we got that curiosity, because that thought just popped in my head that it's when we had said maybe we should have Mrs. Preheim come in here and take pictures for yearbook, but you said no, let's wait till we get that board filled up with different types of compounds. Yeah, smart things, because, okay, in a similar manner, of course, this isn't going to make any sense to you now, but what we're getting at here, okay, there's a double bonded oxygen there on all of these, okay. This would be any type of monosaccharide depending upon where these hydrogen atoms are. And then what happens, okay, is that once you close this loop, okay, you're going to reduce this just like this happened. It goes through a reduction, okay, and then that double bond gets broken. And I always start this with a dashed line. And then what ends up happening is you have a hydrogen and an OH group, very similar to what this is. So now this term of a hemiacetal is the same as what we would see here, because this double bonded oxygen gets reduced. And that's why we save this concept till just right before we start the carbohydrates. Okay. So the process would be the same even if you had a larger aldehyde. Okay, we're going to add, you could even say some ethanol. And I don't know if you'd rather have the molecular formula or there's nothing wrong with doing this. It's just maybe a little more difficult to see what's actually happening, okay? So when we look at this, what is this hydrogen doing to that oxygen? Very similar to up there. It's breaking it. That's a reduction, okay? So now like you said, we're putting these two together. So there's really nothing left over. Okay, like you correctly said, this reduces that oxygen. So now we just have OH. And then what's left over from everything else here? If we could put a box around here to give us a clue. So then what we would see happening is you can write it like this, or I heard someone saying OC2 H what? 5? 1, 2, 3, 4, 5. Okay? Then that's what we get attached here. Okay? All right. Then, of course, you do the same thing with butanol and propanol. Okay? You're just reducing that oxygen and then attaching everything that's left over on the bottom. And then you have your hemiacetal structure. Yes?
How do you know how many carbons to use? Like,
oh, whoops. I'm missing one. Does that answer that? Yeah. I always just see if anybody's paying attention. Okay? Can't get anything past you students. That's good. Whether it's, what did I have up there? Methyl? What was it? Okay. Ha 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 ha. Yeah, something like that. Okay. Now, the last thing, have you had enough for today, or do you want to see the full acetal structure? Or we can do that tomorrow too. But I for sure wanted to do this, okay? So it does say review. We still have to do the full acetal, but we can review naming compounds and we can review reactions. I'm asking for input, so you provide that input. Of the naming. Naming the compounds and the reactions. Okay. So we can go ahead and erase this. Okay.
We'll need to know this for the exam.
For part 2. Yes, on Friday. So that is correct. That is correct. I believe so. Sorry? No, this is not a full acetal. This is a difficult compound to name. At least I think it is. I know, take a deep breath. I am. Oh, you never know. Okay, first of all, what's your organic family? Okay, it's an acid. Okay.
I don't know what that thing is on the bottom.
Okay. Okay. So the reason that this may look really, really difficult is we know that 4 carbons is our parent chain because we've already established that here. But if you did not like seeing the condensed molecular formula, you could change this to what on your paper? To its structural formula instead. And really all you're doing is this carbon is surrounded by how many methyl groups? Right. So you could do this, as long as you do it right. Okay. And then, I don't know, just put a line through there. Okay, now we've got the same thing. We've got our T-butyl group because when we do this, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, the moment that you do that, we know our parent chain is longer than 4, but if you do go up and to the left, you don't know what to call this because this is part of your parent chain because it has to be because that's your organic family. So now that we've established this, this has to be your first carbon, okay? Then B or T? That's a trick question. Got to be careful here because we go by BR here. Here we're going to go by what? T?
B.
Right, that's the trick because it's not just B. B what? Okay, so this has to come after that. So then this actually gets named first on which carbon? Okay. So now we've named this. Now we just have to name this mess down here. Okay. The reason that this can be tricky is because we've got this prefix here. Okay. We do use some prefixes in alphabetization. Hey, I said it right. okay? If it was isopropyl or isobutyl, okay? So I was struggling in my mind, okay, because I was trying to remember, God darn it, I want to write isopropyl, I couldn't remember, and then it just popped in my head, well, I'll just make it a tertiary butyl. So, but anyway, if we wanted to make that isopropyl, okay, there's two different ways you could do that. That's this. That's an isopropyl group, or this, okay? Then, of course, this would get named next because, no, it wouldn't. It'd still come later because you're using the I instead of BR.
So for isopropyl, you use the I.
You do.
But for isobutyl, do you use the I or do you use
Yes, you still do.
Okay.
Yep. So then, how do you draw an isobutyl group? Okay, there is a propyl group. Are we going to put it on here or here? One or two? Kind of playing an optometrist here. Isn't that where they go? One, two. We sure? Really sure? Yeah, that's right. Okay, so there's your isobutyl group. Okay. Then you've seen tertiary butyl. All the way down here is just a butyl group. Okay, there's propyl, there's ethyl, and of course there's methyl. Okay. Okay. Now, what do we have? No, I named this compound. Oh. Yeah. Butanol. Okay. This then is butanol. Okay. So how would 3-butanone be different than butanol? Okay. And that was mean of me to say that, I know. And this is why. Okay. Because there is no such thing as 3-butanone. Typically, we read left to right. Okay. No, that's not 3-butanone. 2-butanone. Okay. Well, yeah, sort of. I don't know. Maybe. And soon, usually about the time, I think the end of March rolls around, we're winding things down so quickly, you really don't, there isn't going to be much left for me to teach you. Not that you can't learn it, but you've learned so much that you really don't need anyone standing up here showing you, telling you what to do. So kind of more like a college-like feel, maybe. Okay. So don't forget how to name aldehydes, ketones, of course acids. We won't put any ethers on there. But do you need ester review?
Yeah, let's do one.
Okay. All right. Then this will be the last thing we do for today. All right. Okay, so I left a space in there for a reason. How do we know we're looking at an ester? Is one or two oxygen or oxygens? Mm-hmm. Okay. All right, there's one. And then, no, I'd rather put it over here. No, I had wrote it down before actually said anything. So, okay. Because again, conventionally, we read left to right. But in this case, are we going to read this from left to right? No, we're not. And how would we know that? Because you're shaking your head, no, that's correct. Why would you know that? Okay, you've got to do the alcohol side first. And the reason that we know that is when this ester gets synthesized, this is your acid side, this is your alcohol side. And this has to come first. And again, this is a derived unit. It really doesn't have a typical parent chain like what we did earlier with butanone and butanal. Instead, again, you name it how. You got to name what first on your alcohol side. Okay, that's true. Okay, yeah, that's true. But we don't name parent chains because this is a derived unit. Okay, so you have to start with the derivative. Okay, so then a 4-carbon derivative is butyl. Okay, so we've established this side. Go from the center, work out. This ethyl group is where? Now we've taken care of our alcohol side. Now our acid side is what? Close. It's Hungary. Yeah, maybe. Because it ate that. Yeah. Okay. Butyl 2-ethyl propanoate. Okay. So we will pick up with this again tomorrow. We'll catch up to you next time.